Welcome everyone. We're going to look at a acid-base question taken from a worksheet on acids and bases given to my classes, and this is question 8. So, the reaction between sulfuric acid, H2SO4, there we go, and a sodium hydroxide solution, so I have a strong acid with a strong base, is investigated using the apparatus below. Are we all good? It's the usual setup. Burette, retort stand, H2SO4 is in the burette. The base is in the Erlenmeyer flask or the conical flask. You might know it as that. Write down the name of the experimental procedure. Please be careful. I didn't ask for the type of reaction. Sodium hydroxide reacting with hydrochloric acid would be called a neutralization reaction. But this is not what they're asking. They're asking for the procedure. What do we call this technique? And here you can either tell me it's a titration, or you can tell me it's volumetric analysis. And we call it volumetric analysis because we're analyzing an unknown using volume to get to know something about it. Okay? What is the function of the burette? Well, it's to measure the exact amount of H2SO4 needed to reach the end point. Now I'm saying I'm measuring the H2SO4 because it is the H2SO4 that is in the burette. Okay, it's in the burette. So I'm using that as, usually in the burette it would be my unknown solution. Okay, there's always exceptions to this, but the general rule is the unknown thing is in the burette, the known thing is in the conical flask. Okay. Then they want, define an acid in terms of the Arrhenius theory. Now, it seems like a lot of questions I've done lately have got this. Please don't take it as a given that that's what you're going to get in your final exams. Your Arrhenius model are acids are substances that produce hydronium ions. In other words, H3O plus ions in solution. Remember, there's also the Bronsted-Lowry definition, and that definition says to us that acids are proton donors. Make sure you read which definition they want. Then they say, give a reason why sulfuric acid is regarded as a strong acid. Well, H2SO4 ionizes completely in water. This is just a roundabout way of asking the definition of a strong acid, which is that strong acids ionize completely in water. But instead of asking for just the general definition of a strong acid, they're going very specifically and they want to know why is H2S a strong acid, so you have to refer to sulfuric acid in your definition. Okay? Then they say bromothiamyl blue is used as an indicator. Write down the color change that takes place on reaching the end point of this titration. Choose between blue to yellow, yellow to blue, green to yellow. Well, green isn't an option here. Okay? Bromothiamyl blue will only be green when it gets to, if it's pH 7. It's not going to start as green. So you need to know that bromothiamyl blue is blue in a base, yellow in an acid. So in other words, it's going to go from blue to yellow. Now we get to the fun questions, which is always the calculations. During a titration, a learner adds 25 centimeters cubed of sodium hydroxide of concentration 0.1 mole per decimeter cubed to an Erlenmeyer flask, the conical flask. Titrates this with H2SO4 of concentration 0.1 moles per decimeter cubed. The balanced reaction that takes place, we like it because they've given us a balanced reaction, so we don't need to worry about it. They want to know the volume of the H2SO4 which must be added to neutralize the NaOH completely. So when I look at the information I've got the volume of the base, 25 centimeters cubed. I've got the concentration of the base, 0.1 moles per decimeter cubed. They gave me the concentration of the acid. And they want to know the volume. Looking at the information I've got, easiest is the ratio value, the ratio equation. So Na over Nb equals Ca over Va, Cb over Vb. So it's a 1 to 2 relationship. We know that's 0.1. I want the volume of the acid, and the base is 0.1 times 25. So my acid is 12.5 centimeters cubed. There we go. That's okay. 4 marks. That's quite nice. It's equation, substitution on both sides, and then final answer. Then we get the question where at this point we all have a little bit of a heart attack, because it says if the learner passes the endpoint by adding 5 centimeters cubed of the same H2SO4 in excess, they want the pH of the solution in the flask. Okay, it should say in the flask, not in the end flask. Now we've got to think carefully about this. Okay, so we add in an extra 5 centimeters cubed. I used 12.5 centimeters cubed. Okay, then I put in an extra 5. What we need to recognize is that we've added in extra moles, and we can't just use the volume. By using more liquid, okay, the final volume of my solution is going to be bigger. Originally, okay, so now follow the reasoning here. We have our flask, okay. In that flask, we had 25 centimeters cubed of the base. To get it exactly to the end point, I added in 12.5 centimeters of the acid. So this final solution was 37.5 centimeters cubed. But I overshoot it by 5. That means I've actually got another 5 centimeters cubed in here. That means my total volume that I'm concerned with is actually going to be the 5 plus the 37.5, which is 42.5 centimeters cubed. So I know the volume. What I need to know is how many moles does this equate to, okay? Because to get pH, I need the number of moles of the H3O plus. We also now need to remember, we reach the end point when the OH minus concentration is equal to the H3O plus concentration. So we added equal amounts. But now I've added more. I've added a lot more. Okay? So what I need to know is how much did I add and how much actually reacted. Alright? And there's more than one way to work this out, but the easiest is this. I added an extra 5 centimeters cubed. I didn't need that extra 5 centimeters cubed. So that is my excess number of moles of acid. So the number of moles of acid that was in excess, this is the extra I put in. This is all my thinking, by the way. Now I'm doing the answer. It's going to be the concentration of the acid times the volume. My acid was 0.1 moles per decimeter cubed, and I added in an extra 5 centimeters cubed. So that's 5 times 10 to the minus 3, which means I have an excess of 5 times 10 to the minus 4 moles of H3O plus ions. But I need the concentration. We're working with, let's see what we're working with, H2SO4, okay? But that actually that is important, okay? That is important because when H2SO4 breaks up, we get 2 H plus ions and 1 SO4 minus ion. That means the number of moles of H3O plus ions that I'm going to get is going to be 5 times 10 to the minus 4 times 2. Twice as many. Okay? Hopefully you're still following me. So this gives me 1 times 10 to the minus 3. Okay? 1 times 10 to the minus 3. Hopefully you're all with me. And you might need to think about that a little bit. Why am I finding this? Because I now can work out the concentration. So now the concentration of the H3O plus ions is number of moles over volume. So it's 1 times 10 to the minus 3 divided by my volume, which was 47,5 times 10 to the minus 3. Alright, so 1 to the minus 3 divided by 47 to the minus 3, and we get 2,11 times 10 to the minus 2. It's not 47, it's 42 and a half. Okay. Thought it looked funny. So it's 42 and a half, which is what we wrote over there. So I think some of you might have got a little bit confused. It's 42 and a half. I do apologize. So let's do that again. Alright, and we get 2,35 times 10 to the minus 2 moles per decimeter cubed. Now that I've got the number of moles, pH is the negative log of the H3O plus ions. So it's the negative log of 2,35 times 10 to the minus 2. And we put this into our calculators. No one expects you to do this in your head. And we get 1,63. I'm happy with the low pH because I added in extra acid. I went beyond the neutralization point. There's extra H3O plus ions. It must be an acidic solution. And I hope that helped.